Okay, let's get started. Are there any questions? You should have most of the data already computed, right? Yeah. Yeah. Yeah, I'm not sure I can help you much with that question. There's definitely something in the API for the data frames to make it easy to do the windowing. Any other questions? Has everyone finally gotten Apache Tori to run on their machine, either in a Docker or directly? Has anyone not been able to get? Then you should talk to Patrick here, who managed to get it compiled for Windows, right? Everyone can get an extension except you, because you already have it running, right? So Patrick here was able to get Apache Tori running on Windows 10. What version of Windows 10? So those people who are still trying to figure out how to get Apache Tori running on Windows, you should talk to him after class. He also put a link on the wiki, which should get you through it, right? The Hadoop's not needed. Is there a problem running Spark on Windows without? The other way. Any other questions or issues? Now, right, we need. So I want to do a couple things today. One is I want to look briefly at Hadoop, so you've seen it, and we've seen some of the differences. And to do so, I want to look at the word count example, since it's a standard example. So basic idea is you have a text file, right? And you're going to break into words, and you want to count how many times each word occurs in the file. We looked at this last time. And so the goal is we're going to use the distributed file system to break the file into smaller pieces. And then we're going to take and separate out the word, split into words. And then what we want to do is we then want to map each word to a tuple. The key is the word, and the value is the number of times that word's occurred. And we start with all ones. And then we're going to use reduce to reduce all those. The first we're going to do reduce on each platform, each worker. And then we have to do the shuffle. We're going to send all the tuples with the same key to a single machine, right? So in this case, we'll send cat to the first worker, we'll send A to the second worker, and we'll send bat and hat to the third worker. And then we can combine to another reduce then by combining all the tuples that have the same key, right? And at that point, we can then either bring all the data, right, to the master or route it to a file. Right? Recall this from last week? Any questions about the idea? Right, so we use a split to do it up. We use a map to, right, take a word and convert it to a tuple, and then we can reduce by key to reduce all the keys, and part of that causes a shuffle to bring all the tuples of the same key to the same machine. And so in Scala, there it is, right? Read the text file, and that returns a data frame, right? And then I can do a flat map onto a split, and then I can do the map to map it from a single word to a tuple word, and then I can reduce by key by adding up the values, and then I can save it. The whole program. So it's 1, 2, 3, 4. It's 5 lines long, right? Job is a longer. So now what I want to do is I want to, I'm going to shuffle. I want to go to Hadoop for a while, and we'll then eventually go back to that problem and say, how do we solve this in Hadoop? Right, so Hadoop is, it's a framework for distributed storage and distributed processing of large data sets, right? Pretty much the same as Spark. It contains a number of pieces. There's some utilities. There's a Hadoop distributed file system, and this is Spark will use this. So when you download Spark, that's why there was one option that said with Hadoop, blah, blah, blah. is for the distributed file system piece, not the whole Hadoop. There's also what they call Yarn, which is a scheduler, deal with clusters, and then there's MapReduce, right? And so this MapReduce part is a part that we're replacing with Spark. So there's 4 big pieces. We can use Yarn with Spark. We use the two files in the Spark. We're just basically swapping out the MapReduce segment. It's also just a Java program, and it also contains some native C code and some shell scripts. So there's a bunch of jar files. And what Patrick did, right, is he compiled some of that C code, right? So, yeah. It also comes with native libraries to do I/O, for compression and I/O, right? And these native libraries only exist on versions of Linux. That's why when you have it running in a window, when you have Spark running in Windows, or you have it on Mac, you'll get this. When you look through the log file, it'll say can't find native libraries using the Java equivalent. If you build, it should go away, but it's not a problem. Things will be a little bit slower, but if you're just using your machine for develop, it's fast enough. But that's what's going on. It's basically they're using C libraries to do this compression and some I/O. And that's the warning you get, right? Unable to load native Hadoop library for your platform using built-in Java. Yeah. Hadoop file system, it's basically a distributed file. The big thing here to note is that the file system is tuned for very large files. Does anyone know the standard block size of a file in Unix? Any version of Unix, Linux? And a typical value? Yeah, so it's like 512K, right? The default in Hadoop file system is 128 megabytes for block size. Wow, because you need fewer blocks, you move big data, and you don't want to have such. The standard file system is designed to handle a huge range, right? Here we're just doing a large range, so let's optimize for that. And you can actually make it larger if you want. And basically, when you add a file, the file system, it'll distribute it for you. And it's the files are read only. And typically, what they'll do is each block they'll send to more than one worker, so that it's replicated. Okay, so that one worker goes down, you have a copy of it, and that's configurable. They've got their own terminology. Their master is what they call the name node. Manage the file system. The clients interact with the name node. It deals with the cluster. And there's Typically on a cluster, there'll be two name nodes, the active one, then a shadow one. So if the main name node goes down, then they will fall back to the shadow one. In Hadoop 3, you can now configure to have more than two name nodes if you really want. And then the workers they call the Datanode. And the Datanode, when it fails, the block it's working on are all stored elsewhere. The configuration file, we configure this. The default for the standalone or pseudo distributed on your local machine is just 1, because you're basically using underlying operating system anyway. Right? So this is different terminology. One thing to know about Hadoop is Hadoop was written in Java, and it was written long before, it was started long before functional programming started to become popular. So it's pure Java. And this was written way before Java 8. So there was no way to do lambdas or pass in a function as an argument, right? So the way you structure Hadoop programs is completely different. So first you write your map function, but it can't be just a function because we don't have functions and we don't have lambdas, we can't pass in. So there's going to be a class, and so inside that class you're going to have a function, a method, right? Which is really our function. Same thing reduce, right? You create a class, and that class, right, has a method which is going to be a reduce function. And then you have to write a main that ties everything together. So here is the map function to do the word count. We also don't have type inference. This is Java, right? So we have to specify all the types, right? And so our mapper function has to extend the mapper class, and that class is generic with 4 parameters. The 4 parameters are, you potentially have a key value pair coming in and a key value pair going out. So the first 2 parameters are the key of incoming map pair and then the value, and then the 2 last ones are the type of the key going out and the type of the value going out. In this case, we don't care. There's no real key coming in. We're just going to read text. And then what we're going to do is, okay, so then we have our key coming in, a possible value coming in. In this case, the value is just going to be the file. And the context is what we write to put the output. And so I take the value and convert it to a string. So now I look at the file as one big string. And I'm using tokenizer to tokenize it into words. And now we want to basically make that pair, right? But we have to tell what type of thing we're going to write out. And it has its own types. So one type is a text. And the other one is a int writable. These are built-in types for Hadoop because they need to know how to efficiently transform them and write them and read them, right? So we don't use Java types anymore. We're using Hadoop types. And then we get to write it out to the context. And what this context does, it writes this out to a temporary file on the worker machine. Does not stay in memory. So how many lines of code was it for the Spark one? And how many lines of code have written so far? It's already more than 5, right? And this is just a map. Now we have a reduce, it's the same thing. We need a subclass reducer, and we have to tell it again. We expect a tuple to come in, and we're going to write a tuple, right? And so in this case, the input is going to be the tuple we just wrote out on our map function. And so the input is a text and int writable. Again, Hadoop types, and then we're going to write out the same thing, right? The text is the key and int writable. And then what's going to happen is a reduce function is going to be called, we're going to get one key, and then we're going to get a bunch, all the values that have the same key. So behind the scenes, what's happened is Hadoop has already combined all the tuples that have the same key, and they pass it to a reduce with the one key and list of all the values. So in this case, we just sum up all those values, and then we write out the result to the context again. Now, what's hidden from us is that our reducer may be called twice, right? Typically, they'll call it on each worker to reduce all the data on the worker, right? And then they have to do the shuffle, right? To send all the key value pairs, the same key, to the same machine. And then we're going to apply it again to finally reduce it so that it's only one copy of each key with the result. So far, so good. But now what we need to do is we need to combine it all together. So we write a main program, which basically tells Hadoop how we want to run our job. And so we create configuration. We tell it what, here is the jar file we want to run, you to run. And then the mapper class. And then there's a combiner class and the reducer class. The combiner is going to be done on each machine, and the reducer will be done overall. And so we're using the same reducer, right? One to reduce it locally before the shuffle, and the other one to do it after the shuffle. And then you have to tell it how are we going to write the output. And then we're reading from the arguments to figure out what file we want to read it from and what file we want to write it to. And that's basically all you can do with Hadoop. So you may end up making multiple passes of the data because you can only do one map and one reduce each time. And so then your main driver, you would say, okay, here's my first job, and when it's done, run this second job and run this third job, right? And so you'll make multiple passes over the data. And if all you have is first a map and then a reduce, if you do anything complicated, you have multiple passes, right? So it's a lot more work and far less interactive. And it's far more limited. To do your current assignment with Hadoop would have been a lot more work. All right, how do you compute the average? Well, you compute the sum, and then you compute how many there are and divide, right? How do you do standard deviation? Oh, that's going to be a real challenge. All you get is map and reduce, right? Whereas Spark is like, well, you just call, there's a function built in, right? So anything that doesn't lend itself to just map and reduce is going to be very painful on Hadoop. And it's going to be a lot slower. Questions? Hope this makes it slightly clearer why we're doing Spark and not Hadoop. If it's not, I can create an assignment to use Hadoop, and then you'll really understand why you never want to do Hadoop. So the question is, when is Hadoop better than Spark? There's supposedly a year ago, there's like 3 answers I found where Hadoop was better than Spark. One thing Hadoop does, which Spark cannot do, is what unfortunately Hadoop calls streaming. And Hadoop streaming has nothing to do with streaming that Spark does. Basically, when you look at this program, there's 3 separate pieces, right? There's the mapper class, and there's a reducer class in the main program. And so what Hadoop has the ability, you can write your mapper in any language you want, as long as that language can read from standard input and write to standard output, right? So if you want to write your mapper in COBOL, and COBOL allows you to read from standard input and write standard output, you can, right? So basically, that means almost any programming language you can write Hadoop programs in. Now the problem with that is the way that works is that Hadoop is written in Java, and so all the data starts in the JVM. And then if you want to send it to your COBOL program or your Fortran program or your Perl program, you have to take all that data out of the JVM, convert it to some format that it can be sent. Well, we know what format it's going to be because it's going to the standard out, so it's a string. So you take all your data, convert it to a string, you send it to another process, that process has to convert that string into numbers or whatever it's supposed to be, right? Do the processing, it has to write out the answer again as a string, right? Which the Java virtual machine has to read in as a string and then convert back to the right format and then write to the disk. And then we repeat this process with the reducer function. It's of dubious value, right? I mean, if the only language you know is Perl, then it's a feature because now you can use Hadoop with Perl. But you're going to pay that penalty, right? Whereas Spark, you basically get, there's Scala, Java, any JVM language, and then Python and R. But both Python and R have the same problem, right? Because any data that's in Spark that you want to bring in and do anything with, right, you have to convert back and forth. So that's one advantage it had. Another advantage it had is that initially Spark only had static allocation, meaning when you ran the Spark program and you said I wanted 10 worker machines, right? All the Spark processes on those 10 machines were active until the program shut down. There's no way if 5 of those machines finished to release that resource. Whereas Hadoop would. As soon as a job finished on a worker machine in Hadoop, it could release that resource so that machine could be used as part of another job. Whereas initially, Spark wouldn't do that. Although now you can do it dynamically in Spark too. But given that Spark is typically 10 times faster, even that's, I mean, you still may be better off running Spark and keeping all the machines active until all of them are done because you're going to be done 10 times faster. And the third advantage I found was that people were saying that Hadoop was a little easier to configure on a cluster. I don't know if that's still true or not. But once you have it up and running, so at this point I consider Hadoop sort of a legacy system, and I've come across people who said, look, we were doing Hadoop and it was a lot of work and slow, and why are we doing this? And then they switched over to Spark and said, oh, it's a lot faster. And Spark relies on pieces of Hadoop, right? But again, the part that's cumbersome with Hadoop is the map reduce part, right? What's that? Yeah. And so, we can use the distributed file system is fine, right? Yarn is fine. So it's just that map reduce part. So it's not like the entire Hadoop system is gone. It's just that map reduce part. You really want to use Spark instead. The one other thing that just keep in mind is that when you run a Hadoop job, right, this main driver, this is what's being run on the master, right? And it's run sequentially. The reduce and map part, they're only run on the worker nodes. And it's run sequentially, right? When we go back to this, right? One thing, when you're dealing with Spark, you have to keep in mind that parts of this code are run on the master and parts of it are run on the workers, right? When we read the text file, it's being run on the workers, right? This flat map, right? That's being done on the workers. When I save as text file, that's an action. It brings it all back to the master, right? So every time you run an action, that action is grabbing all the data and bringing it back to the master, whereas other parts are done in parallel. And I did an example last week where you did the for each, and you compute the sum, right? And it's like sum equals 0, and then for each on a data set, sum equals sum plus the element. And the confusion there was the sum was on the master, right? And the for each was on the workers. And so the sum on the master never got modified. Okay, is that? So that's a Hadoop, right? But now when people start talking about a Hadoop, it's sort of fuzzy what they mean. Because yeah, Hadoop itself, right, is Hadoop Filesystem or HDFS, MapReduce, Yarn. But there's this whole ecosystem of things that exist now. And it goes on and on. There's Tez, Pig, Hype, HBase, Aussie, Falcon, Spark, Zookeeper, Phoenix, Big Top. There's a bunch of others, right? And these are all big systems themselves that do various things. So Pig is a high-level platform for creating Hadoop programs. And so I created this language that they call Pig Latin, which here is the map. Here is the word count program written in Pig Latin, right? So this Pig Latin, you write this high-level language, and it then converts it to a Hadoop setting for you. Why Pig? Well, because Hadoop was too hard to use, right? It was too complicated. It was too painful. So they created this language, high-level language, right, which would basically write Hadoop programs for you. And it sort of makes sense, right? Load means just, right, the file, and then for each, you're going to flatten it and convert it into each word, and then you're going to group them by word, and there's a whole another little language you get to learn, which we won't do. Hive is just, we can use Hive with Spark, but it gives us a SQL-like language to deal with data, and then we can use this language. It could be converted into Hadoop programs. And again, here is the word count program written in Hive. It's another little language we use high level, in part to get around the fact that Hadoop is a little complicated to use and low level, and also because the world knows SQL. HBase, the whole Hadoop thing started because Google wrote this paper about how they're using MapReduce on their big data sets. And a few years later, they wrote this paper on Bigtable. They said, we don't use MapReduce anymore, we use Bigtable. And then, of course, we have to implement Bigtable. And so that's HBase. And it's basically a database for distributed data. And, you know, scoop is basically, you know, allows you to grab data from a relational database and suck it into Hadoop, right? Makes sense. I mean, people, and so Apache Phoenix is basically a huge distributed system, a huge distributed SQL database. And of course, Amazon has their own distributed database that they recommend, which they claim is much faster. There's Spark, right? Hadoop is just MapReduce, and so Mount is basically written on top of Hadoop to machine learning. But since Spark comes with machine learning, we will do that instead. Hadoop is only for batch jobs. And people want to do streaming. You know, if Amazon wants to see what's going on in their business and analyze what's going on, I mean, there's orders coming in 24 hours a day, right? There's no stopping. It's not like the store shuts down at 5 o'clock and then we can see what we did that day and give our manager a report what was selling well or not selling well, right? Amazon has a steady stream of orders coming in and never stops, right? And so if you're doing any sort of analytics on what's happening, it has to be in real time. So you want to stream that data and process it as it comes in. And so Flink and Storm are streaming systems, and we'll look at Spark streaming. And Spark streaming does have a few delays in, so it's not exactly real time. Right? So there's a huge ecosystem out there of various projects that tie into Hadoop or the Hadoop environment. So far, so good. So now that you're almost comfortable with dealing with basic Spark, my next goal is to move on and look at machine learning part of Spark. And once they finish that, we'll go back and look at the streaming part. Right? Before they do that, there's a few other things I'm going to look at before I get the machine learning piece. One of them are distributed variables we get. So currently in Spark, you know about RDDs and data sets. The problem with those are when you have a data frame or an RDD, right? Each worker has their own set of data, but they don't share any information. We can, when we write a Spark program, any local variable in our Spark program, right, is replicated on the workers, and so they get a copy of that. But those values are basically set when we start the program up, right? It's not like we're running along and now here's a a number I want all the workers to have, right? That doesn't work because when you start the workers up, they get a copy of that environment that program sets. And there's no way for workers to send a piece of data back to the main except by the main collecting RDDs or doing an action on a data set. So that's what these distributed variables are meant to do. So there's a broadcast variable, which basically the worker can set, and then the master can set, and all the workers can then read it. And the accumulator, the workers can actually add to it, and then the master can read the result. And these can become useful. The accumulators can be useful in debugging to see what's happening, because now you have each worker can change that and see what's going on. And when you run a Spark program, you can also get the Spark web UI, and you're supposed to show up there too. So at any time, I can create a broadcast variable by Spark or context broadcast, and then give it the value I want, and that will be broadcast to all the workers, and they now have access to that piece of data. And to get that value out of it, you call value on it. And now we can use that. The workers can access that value whenever your code needs to. Right? So it's pretty easy to use. And we can create, here's an example of taking a map and sending that out too, right? But it's just not simple values, but we can send maps and arrays and whatever data types you want. Nothing earth-shattering, but there can times it become useful. And so here's a Spark comes with a number of example programs, which you probably haven't looked at yet. Here's one using the broadcast where it's a program which will be compiled and run not in a notebook, but as a standalone program. All right, so we build our Spark session up, we get our Spark context, how many workers do we want, and then we can broadcast the value, parallelize some data, run a collection for each on it, and right. The accumulator, again, the workers are going to write to it, and the master can read from it. Here's an example of using a long accumulator, and we create a new long accumulator, and then we register it under a name, and in the Spark web UI, that's the name it'll be known under. And then that's how we can access it. And then any worker can add a value to it, and it accumulates the results. Right. So here the workers are just adding one every time they this map function. Each value of this map function is called on, and then in the main master program can then read that value. Again, it's pretty simple. It's just a way of workers being able to do some computation and send that result to And I've seen it used in Hadoop, and this construct was mainly used for debugging to figure out how many times, where is this being called, what value is being called. And there's a shortcut we can basically say, look, here's all my, create a long accumulator, here's a name, and now I can access this value. And then there's a double accumulator, a long accumulator, a collection accumulator, and if you want, you can create your own accumulators by subclassing accumulator v2, and there's a bunch of methods you have to override to make it happen. Right? Nothing earth-shattering. It's not going to help you on your assignment, but you should know it exists. Questions? No. Everyone's bored. Either that or they're working on their assignment, right? Yeah. I could stop early and then you just go back to work, right? Some details on I/O. When you're reading it into a data frame, we've seen some of this before. There's a format, right? A schema we can set. There's a read mode, various options, and the path, right? And we've seen a schema. What we haven't seen is these read modes. There's 3 different read modes, right? And they have to do with what happens when the data that you're reading does not match the schema. What do we do, right? So permissive, this basically means the data is corrupted, it's not what I expect, just make it no. Drop malformed. Whenever you got a record that's malformed, you just don't even read it in, just drop it. And then fail fast says, well, just throw an exception, the program stops. All right? So as an examples, I created a file called ages, and there's a name and an age. The name is a string. The age is supposed to be a number. And so C has a non-number, E is missing a data, and F has a float, right? So then I create my schema, which says name is a string and age is an integer. And then I'm going to set the mode each of 3 times and see what we get, right? So when the mode is permissive, it just says, here's what I get, right? E, the value is null. Well, that makes sense because it's not there. F, it's not a number. And so I get, but then it makes, what do I do with F? So it just makes it null, right? It may not be exactly what you expect. And C becomes null too, right? When you say parallel I/O, meaning what? So the question is there, do we get parallel I/O? And the answer is that is the default, right? So what happens is I have a file, right? When I put it on the file system, the file system takes that file and sends each worker a different part of the file. And so when the worker reads a file, they're doing it all at the same time, but each worker has a different piece of the file. So yes, it's all done in parallel. Now, when you do it on your local machine, you can't tell, right? Because it's the same with writing, yes. So when you, if you haven't tried this, what you should do is just read in a data frame and then write it out to a file. And when you do that, Spark will create a directory with a file you put it in. In that directory, there's going to be several things. One is there's going to be a file called either _success or _failure. And then for each worker you have, there will be a separate file with data in it. So if you set the number of partitions to 5 and on your data frame and you write it out, you'll get 5 separate files because you actually have 5 different parts of that file that were read in and then written out. Any other questions? Now, I perhaps to make it a little more interesting, this is going to come up on your next assignment. Having to deal with these snows and things. When I say drop malformed, right? You know, F and C don't exist, but E does. And then fail fast, you get an exception, right? Because it doesn't work. And you could ask, if you are now to try and compute the average or standard deviation of the ages, what's going to happen on these two, right? There's save modes. And so you can either append to a file, you can overwrite a file, throw an error if it exists, or just ignore. So if it already exists, don't do anything. I believe the default is error if it exists. And oh yes, I almost forgot. One of the options is, if you've got a date, how to format it, or a timestamp, how to format it. Which does lead to the question, one thing about these options where it's like a string, what are the values? So if you go to the API documentation, data frame writer, there's different formats, and in each format, when you open it up, it gives you all the options and what the values are. And so you could do things like give the date format, timestamp format. Do you want to compress the file when you write to it or not? Do you want what to do with, when you write out a null value, what do you want to be written out? Again, nothing earth-shattering, but worth knowing. Questions so far? Why do you use what? What's the difference between a CSV file and a TSV file? Oh, yes. So, right, and so the only difference is what character to use to separate the columns, right? So why do you want to create another whole, right? So just CSV, and then one of the options is what character do you use to separate the files, right? And there should be, oh, there it is, sep, right? And you can, when you read it in, you can specify which character you want to use is used in that file to separate the columns, and you write it out, you can specify, so you get CSV and TSV and semicolon separated or whatever, I mean, right? Right, right. When you start reading Spark, eventually you'll come across there's various other file formats. Parquet or Parquet files. It's a column-oriented file system for Hadoop. Columns are stored in continuous blocks, so they're easy to read in each column, and each column can have its own compression algorithm. So if you're dealing with numbers in one column and strings in the other column, you can use different compression algorithms to be more efficient. And you can then read. You don't have to read it. You can just read it column by column if you want. And so this is when you're dealing with large data sets, it's nice to have a way of compressing files and dealing efficiently. So here's one version of that. And of course, being an open source project, you can't just have one such file system. You have to have multiple ones. There's another one. I think it's Arc. That does similar things, and they have different performance characteristics, and people argue over which one's better or not. But there are multiple different file systems we can use to compress things to make it smaller and more efficient to read and write. And then, of course, there is reading directly from an SQL database. Has anyone not read data from a database using Java? Only one person is willing to admit that he has done that. Everyone else has read data from a database using Java. Well, there's a thing called a JDBC driver, and you need to make sure you download the driver for that particular database because they're all different. And then you need to make sure that driver is in your class path so your Java program can use it. Same thing happens in Scala. So you then need to load that driver, and then you need to configure it to know the name of the database. You might have to get a machine name and a port name, and you might have to give it a username and a password to log on to that database. Once you do all that, then Spark can read data from that database using JDBC. And since it's such a popular thing, since databases are such a popular thing, Spark will do some interesting things with it. The first thing is that when you do a query, Spark will try and push a query down to the database. So instead of reading all the data in the database into Spark and then filtering it, they'll try and filter it at the database side and only suck in the data that satisfies the query. Right? And this happens automatically. So that's a good thing, right? A less good thing is that the default for reading a database in Spark is you do it in one partition, i.e. it's not done in parallel, right? You get it all in one partition, and then processing it is all done on one machine. Not good, right? If we want multiple partitions, we then have to specify with multiple partitions, and we do that with what they call predicates. Why predicates? I don't know. And you basically give it, in this case, I'm going to read the data of this flight information, and one partition is going to get all the ones, right, on India, one destination United States. They'll break it into pieces like that. So we can also, partition on a particular column. So here I'm going to do it on the column name, and then we can start giving how many partitions we want, and then we can also specify the range, right, we want to use, right? So the range is going to go from, in the case, 0 to this number, and it'll divide into 10 equal pieces, and then we'll get multiple partitions. So far, so good. So what do we do with all these nulls and nans and bad values, right? Spark comes what they call the data frame NA functions. And there's basically 3 versions. There's drop, fill, and replace. And there's multiple versions of each one. So drop basically says drop the one. I mean, if there's a null there, get rid of that row. Fill, is we're going to take nulls and nans and replace with a value, and replace all this to do not just nulls and nans, and replace other things. So again, using my 8 example, I'm going to read it in. I'm going to get all these nulls. And now what I can do to call those NA functions is data frame.na, call a function, and just basically I'm going to drop all the ones that have any row that has null or nan in the name. And so there it is, drop any with name. I can then use fill to say just whenever I come across a null or nan, replace with -1. Here I'm specifying another example of replacing it with 0 on specifying which column it's going to come in. And then here's an example of doing map. I'm just taking 10 and replacing it with 5, just to show. Someone asked me in office hours, what's the difference, between, big data, machine learning, and data mining? When we do data mining, yes, we're about cleaning data. Yes. But what's the difference between big data and data mining? One has more data probably, right? But what is data mining, right? You have this data and you're going through it and figuring out what's going on, right? Same things happen with big data, just we're doing larger sets, right? So some of the same things start to happen. And one of the things you get to do is you have to make sure the data is clean. And data is never clean, right? It is never clean. And it's going to, when you work with data, it's just going to drive you nuts because it's just never clean. And there's that little value and that little value and this little value. And it's just, until you do it, you don't understand how painful it is, how much time it takes, right? To trace down all the problems. And eventually you think you got them all and you haven't, right? And so I'm working on creating a data set which has problems, so you have to clean it up, and it will not be nearly as nasty as real life because it's hard to be that good. So next time we'll start looking at machine learning.